Hi, welcome to Chapter 3. Hopefully, these lecture videos are helpful so that you can kind of learn the material as if you were in an actual in-person class. Hopefully, you'll find some benefit to these. And the thing is, you can rewind or fast forward or put it in a higher speed mode, all of those things to make your life a little bit more pleasant. So let's take a look at our slides here, possibly. Bear with me. There we go. So we are going to take a look at measures of central tendency. So this whole chapter is about measures of central tendency. Central tendency is basically a statistical measure that's presented as a value, and is what it does is it defines the center of a distribution. It's some value that can describe that center of the distribution. The distribution meaning like a data set of scores and trying to find the center of that in some way, shape, or form. So the purpose of this is to find the score that's the most representative or the most typical score of that distribution. And we have three types of measures of central tendency. We have the mean, median, and mode. Throughout the rest of this semester, if I ask you for the measures of central tendency, you should know that you're going to be providing me three things: mean, median, and mode. I won't ask, provide me the mean, provide me the mode, provide me the median. I will ask, provide the measures of central tendency, and you need to know that I'm asking for those three things. So let's break these down. First, before we start on talking about the means, uh, let's kind of remind ourselves about the notations, because when we start doing some of these calculations and reporting statistics or parameters, they use different notations, and sometimes they use different equations depending upon whether it's a population or whether it's a sample. So as you can see, as just a little refresher, the populations are using a capital N. A sample size is reported using a lowercase n. And that's really, it's a language. And anytime I ask you, what is the sample size, you won't write out the word sample size. You will put lowercase n equals, and then whatever that sample size is, which is the number of people that participated or the number of observations that we have acquired. So let's now look at the means. So the mean is the same thing as the average of a group of scores. So average and mean mean the same thing. They really do. But in statistics, we often use the term mean. It is the most common reported measure of central tendency that is used. And you've probably heard people say, oh, the averages of something, like the average number of yards that was ran for your football team or something to that extent. Very, very, very common measure of central tendency. It does not always mean it's the best measure of central tendency, but it is the most common. So the computation for the mean, or the calculation of the mean, is really the same, but the notation is different. And that's very important because, again, it's a language. So that's why I had showed you the sample size versus population size, so that it kind of can prepare you to start thinking of those together. So population size, and if you'll notice, the population mean is notated with a mu, which is a Greek symbol. It's like a U with a little tail on the front, um, uh, and then the regular U loop in the back. So this is what you use to report the population mean. It is the sum of x divided by the number of observations. That's all it is. It's really the same calculation as the sample mean, which is notated with a capital M, not a lowercase m, but a capital M. And this is for APA reporting, which we want to start getting used to and corresponding with APA reporting. So it's the sum of x divided by the sample size or the number of scores or number of observations in the sample. So there's two different ways that we report it. So you want to be careful that when you're reading word problems that you're distinguishing, is it a sample or is it a population, so that you know what notations to use, because that is very important. It's part of the language. So let's kind of look at how this works. So I have a little scenario here. Participants must walk, past a scary portion of the campus after dark, and they measure fear in how quickly, in the number of seconds that participants are walking across that portion of the campus. And these are basically our scores or our observations. We have 8.25, 9.75, 5.55, 5.25, 10.25, 6.75, and 8.5. Those are all of our X values. So all of those are X. And so if we count these, it's 1, 2, 3, 4, 5, 6, 7, 8 participants, or 8 observations is what we have. So we know if it's a sample, if we were reporting a sample, we would report there's N equals 8. It's very sloppy, but it is an 8. That is our sample size. So to get our mean, we're going to add up the X values. So we're just going to add up 8.25 plus 9.7 plus 5.5 plus 5 plus 5.25 plus 10.25 plus 6.75 plus 8.5. Once we add all of those up, we are getting the sum of X, which is 59.25. To get our mean, we divide that by 8, the sample size, or if it's a population, the population size. So it doesn't change. It just depends upon whether that's the population or the sample. So if you divide 59.25 by 8, because remember the fraction is basically division, this is the number we come up with, 7.40625. We always round to that second decimal in statistics when we're reporting. I would keep as many decimals as possible until your final answer, then you round to the second decimal. And because this third number right here is a 6, it's 5 or more, we're going to round this 0 up 1. So as you'll notice, our answer, if it's a population, it's mu equals 7.41. If it's a sample, it's m equals 7.41. It's a very, very simple calculation, very simple calculation. We're going to look at mean in a different way, though. Let's look at mean as if we were presented with a frequency distribution table, which is a little different because with that frequency table, here's our possible scores. You could score 5, you could score 4, you could score 3, you can score 2, 1, or 0. And then right here are the frequencies that those scores occur. So we can't just add 5 plus 4 plus 3 plus 2 plus 1 plus 0, because that doesn't account for how many frequencies each of those scores have. So one person scored 5, 4 people scored 4, 3 people scored 3, 2 people scored 2, 1 person scored 1, 0 people scored 0. So our participants, the number of participants or the number of observations, if we would add up our frequencies. So 1 plus 4 plus 3 plus 2 plus 1 plus 0 is 11. And that, in this case, we're talking about a sample. That's our sample size. 11 people participated. There's some common things that I see people do. They use the number of rows as the sample size. So they would use 1, 2, 3, 4, 5, 6 as the sample size, the number of rows. That's inaccurate. Or they add up the raw scores, the possible raw scores, and use that for sum of X, which is right here in the numerator of the equation. But that isn't the sum of X because two people scored 2, so you have to count 2 twice. So a way to do that is basically take your F and multiply it by the score. So in this case, it's F, X times 1. So 5 times 1, 4 times 4, 3 times 3, 2 times 2, 1 times 1, and 0 times 0. So if you'll notice right here, I have like a little box, I'm sorry, that was very sloppy, that shows the sum of F times X, because really this is the sum of F times X to be able to get that. Then you would add those. So 5 plus 16 plus 9 plus 4 plus 1 plus 0 is 35. And then that would go in your numerator. And then the frequencies, you add up the frequencies, and that goes into your denominator. So our mean would be 3.18. And because this is a sample, we report with a capital M. So that's how we would use a frequency table over raw scores. There will be times when you'll see a box of raw scores, and maybe I'll put, here's scores, okay? And I have this box, and I have 3, 4, oops, I don't know why it's erasing, 2, 1, 5, 1, 7, 6, and 0. If you'll notice, these are just rows, these are columns, and there's usually space, plenty of space in between, or you might even see lines in between. There is no F. The only way that you have a frequency table is if you have an F in the heading. Like, see, this F has to be in the heading to show that this is a condensed table, a frequency table. This table is just scores. So in this case, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 scores. So our N equals 9 for this one. And they're just raw scores. So you could just add those up. 3 plus 4 plus 2 plus 1 plus 5 plus 1 plus 7 plus 6 plus 0. It's just done as if it's a raw data set. So that's the way you can tell between a frequency table and just a raw data set, which you will need to distinguish between. So let's take a look at the weighted mean. So there's not just a regular, there's a regular mean, just a simple standard mean, and then there's possibly a weighted mean. And this says it combines 2 sets of scores, but it could be more. Or 2 ... I only give you 2 usually. So 2 or more is what this really should say, or more. I need to go back and adjust those, but hopefully this clarifies it. So if we have 2 samples, if the first sample has 20 scores and the second sample has 35 scores, the sample that has more scores is going to actually have a larger influence on the mean. So you can't just take the mean for the first sample, add it to the mean for the second sample, and then divide by 2, because it's not being balanced then, because in whatever sample has the larger sample size is going to influence the mean more. So first of all, you want to take this, the sum of your first sample group, add it to the sum of the second sample, and then you take that and divide by the sum of the combined sample sizes. So you could also calculate using means. I don't ever give you those problems, but you would basically solve for M. It's the sample mean times the sample size, and then add those individual samples up. But I rarely give you that. But let's take a look at how these would look. So here we have 2 frequency tables, if you'll notice. There's 2 different frequency tables. And bear with me, my pen is not working now suddenly. There it is. I'm making little dots, sorry. We have the first sample, 9 a.m. quiz scores and their frequency. So that's a frequency table. And then the second one is, I'm sorry, the 1 p.m. quiz scores and their frequency. That's a separate sample. So often is what we do is we'll say, you know, sample 1 here, and this is sample 2 here. Okay. I already calculated this f of x's for you. So 5 times 1 is 5, 4 times 4 is 16, 3 times 3 is 9, 2 times 2 is 4, 1 times 1 is 1, 0 times 0 is 0. For this one, the same thing. 5 times 2 for this second sample. 5 times 2 is 10. So think of little equal signs. 4 times 5 equals 20. 3 times 4 equals 12. It's the same over here. 5 times 1 equals 5. See how I'm working those? So you just go down and get those sum of f, or those f times x's. And that way you can come down and add up your sum of x for the first sample, sample 1, and that sum of x is 35. The second sample, add those up. Second sample is 49. If you add up the frequencies, so the frequencies for the sample 1, you add this frequency column, we have a sample size 11. If you add up the frequencies in the second sample, our sample size is 16. So as you know, the sample size of 16 is going to weigh heavier on the weighted mean than a sample size of 11. So now we can just kind of plug and chug, put our 35 where that sum of x for sample 1 is. And so I have a little subtext of 1 to show us. Then you put your 49 here where that second sample is. So I have a subtext of 2. You add those together. And then also for the sample size 1, you're going to put that here. And sample size for 2 is going to be here. Now, if you're adding these, I would not do like in your calculator 34 plus 49 divided by 11 plus 16 just straight across. You want to put parentheses. Parentheses around that addition, parentheses around that addition, parentheses around the numerator, and parentheses around the denominator so that you get the right number in your calculator. You don't have to write that, but you want to enter it that way in your calculator. So you should be getting 3.11 is what you should get. You want to do anytime you have 2 or more samples, you could have 3, 4, 5 samples, you want to calculate it using the weighted mean. So in reality, this here, that dot, dot, dot means you can have more than one sample size or sum of x, and you can have more than one sample size for that one. So now let's kind of look at, so weighted mean also before I move on, there's a little subtext of a W. So capital M subtext W to show us that it's a weighted mean. It's not an individual mean, it's a weighted mean. So that's our first measure of central tendency. So let's look at the second measure of central tendency, which is median. You've probably done this before, like in grade school, or maybe not, or you probably might not remember. But the median is the middle value that splits the distribution into 2 sections. So half of the scores fall above the median, half of the scores fall below. So it divides that into 2 groups. So when we have, if you remember, I talked about with the mean, it's definitely influenced by like outliers, which may be a high number. So if we have the number 1, 2, and 3, and then we also have the number 7, 7 is that outlier because it's so much larger than the other numbers. It's going to weigh things down. If we were to take the median, it would be somewhere between 3 and 7, which we didn't have any scores. So the mean might not be the best measure of central tendency if we have an outlier, a number that falls way outside of the normal data. So when we do have outliers, a number that falls way out or a couple numbers that falls way out outside of the normal and within that data set, the best measure to use is that measure of central tendency. And to get that is what we want to do is first find the position of the median. So how many numbers counted in would we find the median if we had the numbers organized from smallest to lowest? So is what we're going to do is take our sample size and add 1 to it, and then divide that by 2. Is what it does is it splits the data into half, where half of the data is below, half of the data is above. And so it's going to differ, look a little bit different if your sample size or your data set it has an odd number or whether it has an even number. So let's take a look at how that looks. So when the sample size is odd, it's going to be fairly simple because you're not going to have to do any kind of splitting or averaging anything. So in this case, we have a sample size of 5. We have the number 99, the number 66, the number 44, the number 13, and the number 8. Technically, I would say the numbers 8 and 13 are outliers because those are so far below 44, 66, and 99. So those are outliers. So median is a great measure of central tendency because it is probably more represented. So if we were to get the median position, we're going to take that sample size, which is 5, and add 1. So that 5 plus 1 is 6. We divide that by 2 and we get 3. This is a mistake I see students make often, is they just stop here and they report 3. If you look up here, 3 is not represented anywhere. And the lowest number is 8. So 3 is impossible. All that is that tells us where the score is located. So as you notice, these are already ordered highest to lowest. So we're just going to count maybe from left to right. Here's 1 is 99, 2, 3. The third number is 44. It would be the same if we counted from the other direction. 1, 2, 3. So 44 is the third number. So the median is 44. I would just report this because there is no notation for median. I would just say median equals, sorry, it's so sloppy, 44. That's what I would put. Median is 44. There's no notation. Now, when we have an even sample size, so in this case, as you'll notice, bear with me, you'll notice there's 4 scores, 99, 66, 44, and 13. So the median in this case will be a 0.5 solution. So we're going to take the sample size plus 1. So there's a sample size of 4. There's 4 numbers, 4 observations, plus 1 is 5. If we divide that by 2, you get 2.5. Again, that's not your median. That's the position where the median is located. So is what you want to do is count until you find that halfway point. So here's 1, 2, and then here's 2.5 is somewhere in between there. Same as this. 1, 2.5 is in between these two numbers, between 66 and 44. So is what we have to do is we have to find the average of those two scores. So the median is somewhere between the second and third score is what it is. So is what we do is we take the average. So we take 44 plus 66, those two numbers right in the middle that splits, and then divide it by 2, and we get 55. That is where the median is. The median is right in the middle of those two numbers, and it equals 55. That's how I would report it. So it's a little different whether it's odd or even. So here's kind of what I was talking about with outliers really affecting um, our measures of central tendency and why we would want to use the median instead of the mean. So as you'll see, we have a table, and I think sometimes it helps visually. So we have three people who scored two. So here's our X values. Three people, because the line right here is at two. And then we have two people that scored three. But then we have this person, one person over here scored 12, because here's 12 is under that. So notice this is the score three, this is two. If we were to take the mean of these, so we have three people that scored two, so 2 plus 2, right, is 6. And then two people that scored three, so 6 plus 6 is 12. And then one person that scored 12, we would add 12 to that, that'd be 24. And we have a sample size, so 1, 2, 3, 4, 5, 6 people. If we calculated our mean, and we're using a population notation here, our mean would be 4. But nobody scored 4, and there's not even very many people around 4 technically. It's really not a representative of the entire data set is what it is, because this person really is pulling the mean over. So the best representation is for us to calculate that median, and the median is 2.5. So that's where the peak is basically, much more representative than um, using the mean. So whenever you have outliers or your distribution um, is not balanced, you would want to use the median instead of the mean to report measures of central tendency, and we'll review some of that. So the last one is the mode. Mode is the most simple. You've probably done this before. It is just the most frequent or most often seen score. You can have no mode. If all the scores have the same frequency, that would be no mode. Or if you could have more than one mode, if maybe two scores have the same mode and it's the highest frequency, they share the highest frequency, there could be 2 or 3 or 4 modes. You could either have none, one, or multiple when it comes to modes. So here's how we would look at mode. If we just have a raw data set, all we're going to do is count the frequencies. So there's only one person that had a score 2, but we have 1, 2, 3, 4, 5 people scored 3. So I'm going to put here 5 people scored 3. Only one person scored 2. We have 1, 2, 3, 4, 5, 6, 7. I lost count already. 1, 2, 3, 4, 5, 6, 7, 8 people scored 4. Only 4 people scored 5, and only one person scored 6, and one person scored 7. So in this case, the mode is 4 because it occurred the most often. So as you can see, if we look, we can also find the mode from a frequency distribution table. So here we have the scores. All you want to do is look at the frequencies, which frequency is highest. The highest frequency is 4, and then we want to report its score, which is 4. Just happens to be that is 4. Let's look at, maybe I have a frequency table X and F, and I have 3, 2, 1, and 0, and I have 4 people score 3, but 7 people score 2, 0 people score 1, and 5 people score 0. In this case, my mode, because the frequency is the highest for the score of 2, my mode in this case would be mode equals 2. It's not mode equals 7, it's mode equals 2. because 7 is the how many people scored 2. That is something that I see as a common error. So that is the last measure of central tendency. So now let's look at how this works with the shapes of the distribution. I'm sorry, that top part is getting cut off. I'm going to move me down here so that you can read these little boxes. So distributions is just how the data falls, and is what we have is on that bottom axis is our x-axis, the possible scores. On the x or the y-axis is the frequency. And so even though there isn't, we could put this, and this would be frequency, and this is x down here. I will be asking you on homeworks, on the exams, those types of things, how to describe the shape of a distribution. The first thing you want to do right out the gate is look at the distribution. It's a symmetrical distribution if the data peaks in the middle with tails on both sides. Okay, and that's called a unimodal symmetrical distribution. It could also be called a bell-shaped curve or a normal distribution, but it's a symmetrical distribution. You could fold that in half and they would be a reflection of each other when you fold it in half. Another form of a symmetrical distribution is what is called a bimodal distribution. As you can see, there's a peak here and a peak here. On this, there's 2 peaks. They're equal peaks in this valley in the middle. But as long as those peaks are equal, it's a symmetrical distribution, but it's called a bimodal distribution. In this case, is what you have is you have 2 modes, is what is happening there, is you have 2 modes. And typically the mean falls here, unfortunately. So in that case, you would report the mean, but you would discuss that it's a bimodal distribution with modes of, and you would discuss the 2 modes as a secondary measure of central tendency. Below these are skewed distributions. Now this sometimes is confusing. This, if the bulk of the data is on the low end, so kind of think of this as the y-axis here, so the frequency or y, and down here is the x-axis. If the bulk of the data is on the low end with a tail off to the right, it's a positive skew, meaning it's skewing away from the positive numbers or the high numbers, because technically this is 0 and anything below here is negatives. So in this case, it's skewing closer, away from the positive side. On this one, a negative skew is when the bulk of the data, our y-axis is over here. Okay, the bulk of the data is on this high end, and then all of a sudden we have a tail that comes down towards the low end, and that's a negative skew. It's skewed away from the negative side of the graph distribution. So often you can look at those tails and the bulk of the data. I always kind of think of, where does the majority of the data fall to? This is less data over here in this small area than this. This is a large amount of area, okay? So the majority of the data is on the positive side. And so it's skewing away from the lower numbers, the negative side. The bulk of the data here. Very seldom in real social behavioral sciences it doesn't look this perfect. You're going to be presented with some that you're going to have to kind of look at carefully. This is when I say describe the shape of the distribution, you explaining, oh, okay, this here is a positive skew because the bulk of the data is on the left with a tail to the right, is how you would observationally describe that distribution. So I will also ask you to describe the distribution mathematically. That always comes second. First, you describe it observationally, then you describe it mathematically, and you use your mathematical description to either support your visual observation or negate your visual observation. So to be able to mathematically describe your distribution, you're going to subtract the median from the mean. So sometimes it's easier if you go left to right. You're going to take the median from the mean. If your difference is greater than 0, the distribution is positively skewed. If you take the median from the mean and the distribution is less than 0, the distribution is negatively skewed, meaning it's a negative number. If the mean minus median is 0 or very close to 0, the distribution is symmetrical distribution, because that means there's not a difference between the median and the mean. For some of you, if you like to set your math problems up differently, it would look like this. Your mean and your median is like this. Put your line here, and this is going to be the difference. Okay? So you always subtract the lower one from the top one. So this median is always subtracted from the mean. If you flip those, you're talking about discussing the distribution in an opposite manner than it really is. And that's why you need to coincide your mathematical discussion or your mathematical calculation of the distribution shape and coincide that with the observational shape. So some of the questions that you want to ask yourself when you're looking at it observationally is, where is the bulk of the data? Here we're this is the first thing you do. Is the tail on one side or both sides? If there is a tail, which way is it pointing? Can the distribution be folded to show a mirror image? So those are questions that you're going to ask. So if it can be folded to show a mirror image, that's a symmetrical distribution. And so which way the tail is pointing and the bulk of the data is going to tell you those distribution shapes as well. So let's kind of look at this in a different manner. Oops, let me go back. Sorry, is what I was trying to do was move me back up here so you can see. So here's what a symmetrical distribution looks like. If we're looking at a histogram, it's also known as a bell-shaped or normal distribution. In this case, the mean, median, and mode all would be right down the middle, and they would be the same, 5, 5, and 5, because it's an exact mirror image on both sides. That symmetrical distribution has tails on both ends. So we have a tail pointing this way, but we also have a tail pointing this way. And those tails are pretty equivalent, like in size. The next, we have looking at distributions and how you would respond if I asked you to describe the shape of the distribution observationally and mathematically. And as you can see, I have that question in red up here because that's a question you would be asked. So for this, the first thing I'm going to do is describe it observationally, not mathematically first. First thing I do is observational description. So if you can see, I put observationally, the distribution appears to be a symmetrical distribution as the data piles in the middle with tails on both sides. And then you're going to take the mathematical calculation and confirm whether that observation is accurate. And so I said this symmetrical distribution is confirmed mathematically as the difference between the mean minus the median is 0. And as you notice, I have the little calculation here. There should be a parenthesis there. But the mean minus median is 0. So that confirms your symmetrical distribution. And the reason you know this is because up here at the top, I've got those measures of central tendency in a little box for you at the top to be able to calculate that. And you would not use the mode. It's just the mean and median for that. So another one is another example. So here we have a distribution. And if we were describing this, if you look at this, I'd say a positive skew because the bulk of the data is on this high end and we have the tail to the right. We're skewing away from the high numbers, which are more positive. Over here, our numbers start becoming negative, right? -1, -2. So it's skewed toward if you see it's skewed away from those high numbers. The majority of the data is on that left-hand side. I always put this little skier guy in there because I say if you were skiing, would you want to ski towards the positive numbers? Like, see how he's facing that way? Or would you want to be up here and fall off the cliff to the negative side? You would want to ski towards the positive. You don't want to go off that cliff. So think of which way is your skier going? Skier is going to go positive, so that's a positive distribution. Okay, now we want to confirm mathematically. I confirmed it because the positive skew is confirmed because the difference between the mean and median is positive. So if we subtract 2.5 from 3, it is a positive number. So 3 minus 2.5, right, is 0.5. That's a positive, right? So it's a positive skew. It's confirming that. Same thing if we are looking at the opposite. Look at where my skier is going now. He is heading for the negative side, right? He's like, no way do I want to fall off that cliff over here. You know, see where those numbers, you don't want to fall off that cliff. You want to ski towards the negative numbers, right? So it's a negative skew. And so I'm describing that the distribution appears to be a negative skew as the majority of the data piles on the high end with the tail to the, well, this actually should say the tail to the left. I did not catch this. We'll mark that out left. Okay. It is confirmed mathematically because if we take the difference, it's a negative value. So if we were to take the mean of 7 and we subtract 7.5 from 7, our answer is -0.5. That negative difference confirms the negative skew. So you will be asked those questions. I will expect you to describe observationally first and then confirm or negate it with your mathematical description. Now, sometimes if there's a very, very small difference, in this case, the range of data is pretty close together. So 0.5 is a large enough to show a skewed distribution. But if I had a range of numbers that was between 0 and 100, a 0.5 difference is not a big deal. So if you had 0.5 difference and it looks symmetrical, that difference of 0.5 probably just confirms that it's very close to a symmetrical distribution. So those are things that you will learn as you go. So just as a reflection, I will ask you what is the most appropriate or measure of central tendency for specific types of data. For normal distributions of data that are quantitative data, normal distributions of data that's quantitative or close to normal, the mean is the best measure of central tendency to report. It's the most common, and it is the best measure of central tendency. It is used for quantitative data overall, the mean is. That's going to be your go-to measure of central tendency, unless the data is skewed. Now, if you have skewed distributions, the quantitative data that is skewed, you're going to report the median. So if it is skewed pretty dramatically and it's not close to being symmetrical, you would report the median first and foremost. That is the best measure of central tendency. And that's because of outliers. If I was to calculate like the average income in, let's just say Arizona, I would probably get back if I calculated every person's annual income. I would probably get somewhere like 100,000, 125, 130,000. It's just an estimate. But that's probably skewed because there are people that make a lot more than that. There are people that make five, six, seven, $800,000 a year. The majority of us, or whoever, the majority of the population is probably um, much lower than 130,000 a year. So if I said, "Oh, the average income in Arizona is 130,000," that's probably really not reflective of the majority of people. So is what I would want to do is report the median. And the median, I think, is somewhere like 62,000, 65,000. That's much more representative, closer to the majority of what the majority of people make annually. The mode, the only time that we report mode is if it's nominal or ordinal data, is the most frequent. It says nominal data, but it's also ordinal data. Um, Discrete data is really the key, discrete or categorical data. Or if we have a bimodal distribution, if we have a symmetrical distribution that's bimodal, we would report the mean, but then we would also report the modes. And if any other time you have a discrete data, you're going to report the mode over the other measures essential tendency. So there is a time and a place for reporting measures essential tendency. Hopefully that helped. This was probably one of the longer lectures, but if you have any questions, please feel free to reach out to me by email.